Hello everyone, welcome to Applied Chemistry Tutorials. Today we'll talk about 5 different problems related to sp3, sp2 and sp hybridization. Let's start with the first problem. Mention the hybridization of each carbon atom in the following molecules. There are 4 different compounds. The first one is a hydrocarbon. It's a condensed structural formula. If we expand it, there are 4 different carbon atoms. They are attached with hydrogen atoms, and we are now attaching it first using the single bond with another carbon atoms. Now to satisfy the carbon tetravalency, suppose for this one it requires 2 more bonds, so it should be triple bond. So now if we satisfy all the tetravalencies of all 4 carbon atom, it should look like this. So now these 2 carbon atoms are triple bonded, so any triple bonded carbon atoms are sp hybridized, so these 2 will be sp hybridized. Now any double bonded carbon atoms are sp2 hybridized, so these 2 carbon atoms will be sp2 hybridized, as you can see here. Now for the next example, CH2O, which is an aldehyde, there is a carbon which is attached with 2 hydrogen and the oxygen is attached using the double bond, so this carbon will be sp2 hybridized. Now for the next example, this acetic acid, there are 2 carbon atoms and they are attached with several hydrogen and oxygen like this. Now for this carbon atom, it is attached with oxygen using the double bond, so it will be sp2 hybridized, and this carbon atom is attached with 3 different hydrogen and 1 carbon atom all using the single bond, so it will be sp3 hybridized. Now for the next example, you can see there is a C6H5, so this is a phenyl ring and then 2 carbons are attached to it. So the structure is like this. Now to satisfy the tetravalency of this 2 carbon, there will be a triple bond. So any triple bonded carbon atoms are sp hybridized, so these 2 will be sp hybridized, and the phenyl ring carbons are, since they are double bonded carbons, so they are all sp2 hybridized, as you can see here. Now moving forward to the next problem. Are all atoms of propylene molecule coplanar? The propylene structure is CH3CH2. If we expand it, it will look like this. Now if we number the carbon atoms, now C1 and C2, these 2 carbon atoms are double bonded. So they are sp2 hybridized and they are coplanar. Now C3, it is attached with C2, but these all are single bonds, so this is sp3 hybridized carbon atom, but since it is attached with C2, which is a sp2 hybridized carbon, so it will be coplanar with C1 and C2. The reason behind this, any bond rotation around the double bond is prohibited. You can see the reason in our previous lecture. I will attach the card here. You can go back and check. But the reason in short is for C1 and C2, each of this atom has unhybridized p orbital which are parallel to each other and partially overlapping to make this pi bond. So the bond rotation is prohibited, otherwise the pi bond won't be formed. Now if you see the hydrogen atoms and numbered them from H1 to H6, H1, H2 and H3 are attached with C1 and C2, both are sp2 hybridized, so they must be on the same plane to follow the rule that rotation around the double bond is prohibited. Now H4, H5, H6, they are attached with sp3 hybridized carbon atom, so they are forming the tetrahedral structure, as you can see here, around this carbon atom. Okay, so H4, H5, H6 are not coplanar with the rest of the molecule. Now the problem 3. Indicate which molecules are coplanar: ethyl benzene, styrene and phenylacetylene. Please notice that all of these 3 molecules has phenyl ring in it, and there are 2 carbon attached to this phenyl ring. For the first example, ethyl benzene, as you can see, these 2 carbon are all single bondedly attached with hydrogen and other carbon atoms. But suppose for this carbon, although this is sp3 hybridized because single bonded, but it is attached with sp2 hybridized carbon atom of the phenyl ring, so it will be on the same plane as like the phenyl ring. Okay, but for this carbon atom, this is also sp3 hybridized, but this is attached with another sp3 hybridized carbon atom, so it need not to be on the same plane. So this sp2 hybridized carbon atom the hydrogen attached to it, and this carbon atom will be on the same plane, but rest of the hydrogen carbons are attached with either attached with sp3 hybridized carbon, so they won't be on the same plane. So the molecule is a non-planar. Now coming to the styrene structure is like this. There is a C double bond C attached with phenyl ring. Now C double bond C are sp2 hybridized, and the phenyl ring carbons are also sp2 hybridized. Okay. Now this carbon is attached with another sp2 hybridized carbon. Now free rotation around the double bond is prohibited. So all of these carbon atoms are on the same plane, and so are this hydrogen atom for the same reason, because they are attached now with the sp2 hybridized carbon atom. So this is a planar molecule. Now coming to the phenyl acetylene C6H5CCH. There is a C triple bond C. So of course these two carbons are sp hybridized. Now each of these carbon atoms has two unhybridized p orbitals which are parallel to each other, and they partially overlap to make two different pi bonds, so that triple bonds are formed. So of course the bond rotation around this triple bond is prohibited. So this 6 carbon are sp2 hybridized and these 2 carbon are sp hybridized. But since the bond rotation is prohibited, so all these 8 carbon atoms including this hydrogen atom are on the same plane. So this is a planar structure. Now moving forward to the next problem. Compare the structures of methane and chloroform molecules. So methane is CH4, chloroform is CH3. Methane CH4 means it is a symmetric tetrahedral structure like this, but chloroform has two different atoms attached with carbon, hydrogen and chlorine. Chlorine size is bigger than hydrogen, so it is a distorted tetrahedral structure. Okay. Now let's first see the symmetric tetrahedral structure parameters. The bond angle HCH, it is 190 degrees in 28 minutes. Bond length CH, bond length is 1.09 angstrom. For the chloroform, in the distorted tetrahedral structure, there is a chlorine atoms which are bigger in size. So they usually, when they are close to each other, they usually repulse each other, which is called steric hindrance. Okay. So this ClCCl bond angle is now increased to 111 degree, whereas this HCCl bond angle is decreased to 108 degree. Now if we see the bond length, CH bond length is just like regular one, 1.09 angstrom, but CCl bond length is increased to 1.76 angstrom because Cl is a bigger atom, so its atomic radius is higher, so the bond length is also high. So we saw that bigger chlorine atom is causing the steric hindrance, so the bond angle increases and the structure becomes distorted tetrahedral structure. Now to the last problem, problem 5. In which of the following molecules hindrance to rotation is minimum? Acetylene, ethylene, ethane and hexabromoethane. All these 4 compounds are 2 carbon compounds, like has 2 carbon in it. Now for the first one, there is a triple bond in acetylene and any bond rotation around the triple bond is prohibited. So the hindrance to rotation is maximum for acetylene. Now for the ethylene, it also has a double bond. Okay, the bond multiplicity is more than, it's not single bond but a double bond. So the rotation is around the double bond is prohibited. For ethane, all these carbon atoms are single bondedly attached with other hydrogen atom and other carbon atom. So rotation is possible, of course, around the C single bond C. For the hexabromoethane, all these hydrogen atoms are now replaced with bromine atom. Now bromine atom is again a bulky atom, so it causes steric hindrance, as I just explained in the previous slide. Okay, so it will hinder the rotation around the C single bond C because of the steric hindrance. So there will be some kind of hindrance to rotation. So among these 4 compounds, the hindrance to rotation is minimum for ethane. So that's all for today's lecture. Thank you for listening. Please stay tuned with us for the next video.